The presenter is Cristopher Ubal. Affiliation is Eindhoven University of Technology, and the floor is yours, Christopher. Thank you.
Okay. Hello, everybody. Thank you so much for attending this presentation. In this presentation, I'm going to talk about towards detailed chemistry in SU2, coupling the open source Cantera library. So this work has been in collaboration with my two supervisors, Jeroen van Hooyen and Nijso Bijhausen from Eindhoven University of Technology and Bosch Thermotechnology. So first of all, the implementation of combustion using the flame-generated manifold approach, which is a tabulated chemistry, has been already implemented in SU2. So now in SU2, we can simulate premix and partially premixed flames, including preferential diffusion, and also we can use the discrete adjoint solver in these simulations. However, if we would like to obtain more accurate simulation, we require to have detailed chemistry in SU2. Unfortunately, this is still not possible to do in SU2. So we propose a solution to couple the thermochemical library Cantera in SU2. So by the way, this is what we can already do in SU2 using the FEM with a preferential diffusion terms. So what is Cantera? Well, Cantera is an open source for problems which involves chemical kinetics and thermodynamics and transfer processes. For combustion applications, the thermochemical properties strongly depends on temperature. So if we would like to perform detailed chemistry, we will need to get the information from NASA polynomials in order to compute, for instance, the heat capacity. At the same time, in combustion, we require a chemical reaction mechanisms which may contain hundreds of species. As you can see here, this is a well-known chemical mechanism, the GRI 3.0, where we have 53 chemical species and 325 reactions. So for each of these chemical species, we should add is a source term in the species transfer equations. The source term is the sum of the individual source terms that comes out in the M reaction equations, and each source term is computed using this expression, and the rate constants, the K factor here, are usually modeled using the Arrhenius law. So if we would like to do detailed chemistry, we should program all these terms in SU2 and also try to get the information from this chemical reaction mechanism, which has a specific format. So instead of doing that, we can use Cantera, and in Cantera, all this implementation is already, so we can immediately get the source term from Cantera and add this source term to the species transfer equations. So what is the Cantera model? Well, Cantera uses the ideal gas mixture laws at the same as we use in the already implemented fluid model in SU2. However, Cantera, we can get the NASA polynomial for heat capacity and get this heat capacity in this way. We can also retrieve the information from viscosity, thermal conductivity, which are temperature and composition dependent. And regarding the diffusivity models, we already have in SU2 the unity Lewis, which is given by this expression. But from Cantera, we can get an additional diffusivity model, which is mixture average, which is based on this expression, and this one cannot be implemented in the fluid mixture model. how to use the Cantera model. First, we must enable Cantera using this option, fluid model equal fluid Cantera. One advantage of using Cantera is that we don't need to specify any fluid property for each species because these fluid properties are retrieved from Cantera. For the viscosity and thermal conductivity model, we can just call Cantera and compute these two ones. And from the diffusivity models, we have the unit Lewis from the fluid mixture and the mixture average. That is a new option that we can get from Cantera. So now we have new options that are we can provide the gas composition and we can explicitly tell to the solver which species are going to be solved and in which order. We can also read the chemical mechanism file. We can also read the phase name, which is usually the ideal gas, but some mechanism has their equations of state. And we can also provide the transfer model with which we are going to compute the thermochemical properties. So first, we want to test if we can get the same values as the values that the Python version of Cantera provide. So in order to do that, in order to compare the values that we can obtain from SU2 and from the Cantera version and the Python version of Cantera, we first test gas composition of hydrogen, oxygen, and nitrogen. We use a chemical mechanism, which is H2O2, and we use this phase name and the transfer model mixture average. So at both inlets, we provide the same mixture composition, which has equivalence rate of 0.7. So we do that because we want to measure the density and the heat capacity at one inlet and compare with the value provided by Cantera using Python. So if we perform this simulation, we can observe the following, that this is the summary that the Python version of Cantera provides, where we can get the density, and in SU2 we can get the same value of density at the inlet, as you can see here. Also, if we compare the heat capacity, we can also retrieve the same value that Cantera provides. So with this, we have checked that we are retrieving the same values at Cantera Python. Now, we want to check how the Cantera model works with the already implemented fluid mixture model in SU2. So in order to do that, we are going to change the chemical mechanism in order to check that we are able to read another chemical mechanism. This one is the grid 3.0. We are going to consider a mixture of hydrogen and methane. And in order to test both, we are going to use the diffusivity model unity Lewis. So at the first inlet, we have a mixture that has a 0.5 content of hydrogen and 0.5 content of methane. And at the other inlet, we have a mixture of higher hydrogen content, 0.6, and methane content of 0.4. So we already implemented the ideal gas mixture loss in fluid mixture. If we run this test case, we should expect the same output in both in Cantera and fluid mixture. So if we compare what we from Cantera and what we get from fluid mixture, we observe that both solutions are basically the same. So that means that that Cantera model is correctly coupled to SU2. Finally, we can test the unity Lewis and diffusion model with the mixture average diffusivity model that we can get from Cantera. So in order to highlight this mixture average, we use a gas composition of hydrogen, oxygen, and nitrogen. We again do this chemical mechanism, the H2O2. At inlet 1, we provide a mixture with equivalence rate of 0.5. In inlet 2, we provide a mixture with equivalent rate of 0.7. This means that the high and the hydrogen content heat is higher than the other one. So here we should see we should expect a different behavior in the mass fraction of hydrogen, because hydrogen has a higher diffusivity than the other two species. So if we run the simulation, we observe that the picture average model provide a different solution that the simulation using the unity Lewis. This is because the unity Lewis assume that the diffusivity of all the species are the same, and here the mixture average highlight the fact that the hydrogen has a higher diffusivity. So using the mixture model from Cantera, we should expect better result than using the unity Lewis. So this is a good output from Cantera. So what is the next step in this project? Is that first we need the chemicals. Currently, in the species transfer, we this equation, and we have to add this source term from Cantera. And at the same time, because the system is temperature dependent, we have to update the energy equation for incompressible flow. In SU2, we currently solve an equation for a perfect gas where we solve for temperature. This is the equation that we currently solve in SU2 compressible flows. However, for real gases and for combustion application, we should solve equation for the total enthalpy, where the total enthalpy is given by this expression. And now with Cantera, we can retrieve these values because these ones are in Cantera, and we have to update the energy equation in order to solve this equation instead of this one. The part of this work was already presented in the previous SU2 conference in 2023. So now we are going to combine both. So as a main summary, that Cantera for multi-component flow is coupled to SU2. We have verified and validated that we have validated with the fluid mixture model in SU2 that Cantera is providing the expected result. And we can now use a new feature of Cantera, such as retrieving the information from the chemical reaction mechanism and use an additional and better diffusivity model. What to be done in the future is to make a pull request this new fluid. The next step, as I explained, is to combine the extension of the preconditioning plus plus adding the chemical source term to the species transfer equation. So thank you so much for the presentation.
Well done, Christopher. We have seen another interesting coupling between open source codes. Excellent work. Any questions from the public? Evert. And maybe we should mention the affiliation for the public and the people who do not know you.
I see. Well, my name is Evert. I am from materials, working at the Boston machinery and the combustion department. I have a question regarding one of the settings that you presented. You said showed that you could set the gas composition dates. Does that mean that only the transport of the species is available? And if so, what happens to the other species in the picture?
Have you heard the question?
The last part, what do you mean with different species? Sorry.
Well, for example, the H2O2 mechanism is like 8 or 9 species, but if you specify that only 3 species in the conflict, what happens to the other 19?
This is now we are solving for these 3 species. The other ones are 0 at that moment, just for simplicity. But we expect that this fluid model Cantera will be mainly used for combustion. So we expect to solve the complete set of species that the chemical mechanism may have. Yes, and this is just now is for testing. Thank you so much for your question.
Any other question? Maybe then I have a question. I don't know if it's too far-fetching. I and the group and my group have been working on non-ideal compressible fluid dynamics, meaning with fluids that do not obey the ideal gas law. How difficult would it be to extend the work you have done to cover chemical reactions with non-ideal gases? Non-ideal, the equation of state is more complex than PV equal RT.
Yes, thank you so much. There are some chemical mechanisms that allow to use a different equation of a state. So it should not be so difficult. But
from the point of view of the solver, how much? Because I've seen you have to modify the energy equation.
Yes, and for the yes, that will be a problem. We tried with a bachelor student at the beginning of this year to extend the fluid mixture for compressible flows, but we faced some issues, particularly at the walls.
Okay.
So we observed some issues that we should solve before moving to that. Like we observed that the temperature, there is an increase of temperature at the walls where there shouldn't be that increase of temperature. I think that was also pointed by some guy from Nemo in the SU2 GitHub.
Yeah. Thank you very much, Christopher.
Thank you so much for your question.
I'm asking if there are other questions. If not, we can go on with the next presenter.